Welcome to the Spatium channel. Imagine this, right now, as you sit still, reading each line of this text. The Earth is not standing still. We, this entire planet, are moving through space at a speed of about 2.2 million kilometers per hour, a velocity large enough to tear apart any spacecraft ever built by humans. And yet, you feel nothing. No vibration, no wind, no sign that this motion even exists. And even more strangely, that journey is not random. Around 100,000 galaxies, including our own, are drifting in the same direction, towards something invisible, massive, hidden behind the thick dust of the Milky Way itself. A gravitational pull so strong that it draws entire cosmic structures closer, yet lies in a region we can barely observe. We call it the Great Attractor, a name that sounds like science fiction but is entirely real. Now, return to your own perception. You are sitting still. Your cup of coffee is perfectly calm. The space around you is quiet, and yet, in reality, you are moving at a speed the human brain cannot truly comprehend. Start with the most familiar layer of motion. The Earth orbits the Sun along a path of about 940 million kilometers per year, corresponding to a speed of roughly 108,000 kilometers per hour. But because everything around you, the air, the oceans, the ground, is moving together, you do not notice it. Just like sitting inside a smoothly moving car, you feel no wind unless the window is open. But that is only the first layer. The solar system, along with Earth, is also orbiting the center of the Milky Way. One full orbit takes about 225 million years, which means the last time we were at this exact position in the galaxy, dinosaurs had not yet fully appeared on Earth. To maintain that orbit, the entire solar system must move at around 800,000 kilometers per hour, and you still feel nothing. But the story does not stop there. The Milky Way, a galaxy containing hundreds of billions of stars, is not standing still either. It, together with the Andromeda Galaxy, the Triangulum Galaxy, and dozens of smaller galaxies, forms a cluster called the Local Group. And this entire group is moving. Scientists measure this motion by comparing our position to something very special. The oldest light in the universe, the afterglow of the Big Bang. The result shows the Local Group is moving at about 630 kilometers per second, equivalent to more than 2.2 million kilometers, Ho-Taish. In the time it takes you to read a short sentence, everything you have ever known has moved dozens of kilometers through space. What makes this truly thought-provoking is the direction. We are not drifting randomly. Our entire galaxy cluster is moving toward a specific region in the southern sky. Something is pulling us, or perhaps something behind us is pushing us forward. Scientists are not yet completely certain about the exact mechanism, but what they do know is this flow is real, its direction is measurable, and its cause remains a major mystery. The questions begin to form. What kind of object could generate a gravitational force strong enough to pull an entire group of galaxies spanning millions of light years? How massive must it be? And why has humanity only discovered it relatively recently? The answer did not come immediately. It took decades, new instruments that had never existed before, and a group of scientists willing to pursue an idea once considered impossible to slowly assemble this picture. And it all began with something that seems almost simple: the oldest light in the universe. What they were building would do more than explain our motion through space. It would give the Milky Way something it had never formally possessed before: a larger cosmic address. But to understand how that became possible, astronomers first had to solve a difficult measurement problem. When we observe a distant galaxy, the speed we detect is a combination of two different motions blended together. One part comes from the general expansion of the universe, which carries galaxies away from one another. The other part is the galaxy's own peculiar velocity, its individual motion through space, caused by the gravitational pull of nearby structures. To separate those two effects, researchers need an independent way to determine distance. Once the true distance is known, the expected Hubble expansion can be calculated and removed, leaving behind the galaxy's genuine motion through the surrounding gravitational landscape. In principle, the method sounds straightforward. In practice, doing it for thousands of galaxies scattered across hundreds of millions of light-years is a monumental task. That was exactly the challenge taken up in the early 2000s by R. Brent Tully and Hélène Courtois, whose project became known as Cosmic Flows. Their aim was to assemble the most precise and extensive catalogue of galaxy distances and peculiar velocities ever created, then use it to reconstruct the velocity field of the local universe. The first stage of the project proved the method could work on a large scale. Cosmic Flows 2 dramatically expanded the effort, collecting measurements for more than 8,000 galaxies. Later versions, Cosmic Flows 3 and Cosmic Flows 4, extended the map to tens of thousands of galaxies across an even greater volume of space. What emerged from that work was not merely a list of galaxy speeds, but something like a gravitational atlas. Wherever matter is densely concentrated, galaxy motions tend to converge. Wherever matter is sparse, galaxies stream outward toward emptier regions. The velocity field, in other words, acts like a topographic map of invisible gravity, tracing valleys, slopes, and basins across the universe. As Tully and Courtois refined that map, they began to see that the local cosmos was not arranged as a loose scatter of isolated clusters. It was organized hierarchically. Clusters were embedded inside superclusters, and superclusters themselves belonged to much larger flow basins. The nearby universe was turning out to be a nested structure of motions, where galaxies followed coherent patterns on scales far beyond what had once been expected. One structure in particular stood out so clearly in the cosmic flows to data that it demanded a name of its own. In 2014, a paper led by Tully and published in Nature presented a striking result. The Milky Way belongs to a single immense gravitational superstructure stretching roughly 520 million light-years across, containing more than 100,000 galaxies and a total mass of about 17 times that of the Sunday. They called it Laniakea, a Hawaiian name meaning immeasurable heaven. What the study showed was not simply that galaxies near us are grouped together, but that they share a common destination within one vast gravitational basin. The team used a watershed-style mathematical technique, similar to the way geographers define drainage basins on a landscape. In the same way that raindrops on a mountain slope eventually flow toward one valley or another, galaxies in the cosmic velocity field can be sorted by the direction their motions ultimately lead. Following those flows revealed the boundaries of Laniakea. The Milky Way lies within it. The region of the Great Attractor, centered near the Norma cluster, sits close to its gravitational heart. The Shapley supercluster lies beyond its far edge, outside the basin, exerting influence from beyond the boundary. The implication was profound. The Milky Way had always been part of Laniakea, but no one had previously recognized that larger entity as a coherent structure. Before this, our largest familiar context had been the local group, a gathering of around 60 galaxies spread across roughly 10 million light-years. Beyond that was the Virgo supercluster, a broader and less sharply defined environment. Laniakea absorbed Virgo into a much larger gravitational framework and revealed that what had once seemed like our grandest neighborhood was actually just one district within something vastly bigger. It was as though humanity had known its street and city, perhaps even its country, and only now discovered the continent beneath all of them. Publicly, the result was appealing because it offered a new cosmic address: Earth, Solar System, Milky Way, Local Group, Laniakea. But inside the scientific community, Another detail mattered even more. Laniakea explained much of the velocity budget of the local group, yet not all of it. The Great Attractor and the Shapley supercluster together accounted for most of our measured motion of about 630 kilometers per second. Most, however, is not the same as all. A small but persistent remainder remained unexplained. That residual velocity was not large enough to sound dramatic to a general audience, but in cosmology, even a few tens of kilometers per second is meaningful. It implies that part of the gravitational story is still missing. Yehuda Hoffman and his collaborators approached the cosmic flows, two data with a different method, using a Wiener filter reconstruction to infer the full density field from the observed peculiar velocities, even in regions where observations were sparse or incomplete. Instead of searching for another hidden concentration of mass, their analysis revealed something else entirely: a vast underdense region, a cosmic void, lying in roughly the opposite direction from the Great Attractor. This changed the interpretation of our motion. If dense matter ahead can pull us forward, then an enormous emptiness behind us can contribute by allowing matter to drain away from it, effectively acting like a push. It does not repel in the ordinary sense, but in a universe where gravity reflects contrasts in density, a deep void creates a gravitational deficit. Galaxies flow away from that deficit toward denser surroundings, and from our perspective, that outward drainage appears as a repelling effect. The result was a major conceptual shift. For decades, the story had been framed entirely in terms of attraction. What massive structures are pulling us? Hoffman's reconstruction showed that the answer was only half complete. Our motion is shaped not only by what lies in front of us, but also by what is absent behind us. The missing piece was not more mass, but less. In 2017, Hoffman's team published this result in Nature Astronomy and named the structure the dipole repeller. It lies almost opposite the Shapley supercluster on the sky and extends across roughly 700 to 740 million light-years. This enormous void contains far fewer galaxies and clusters than average, and its influence on our motion appears to be comparable in scale to the pull exerted by Shapley itself. That meant a substantial fraction of the Milky Way's large-scale velocity was not produced by falling toward a massive attractor, but by moving away from an immense emptiness. The universe, in that view, does not guide galaxies only through the pull of crowded regions. It also shapes them through the absence left by emptier ones. That realization altered the framework for understanding our cosmic motion. Yet even that was not the end of the story, because there remained another serious problem. Part of the sky is still hidden from us. The zone of avoidance, created by the dense band of stars, gas, and dust in the Milky Way's own disk, obscures roughly 20% of the sky from ordinary optical observations. For much of modern astronomy, the universe behind that galactic wall remained largely concealed. Astronomers tried to work around the problem with infrared and radio observations, which can penetrate dust better than visible light. By the early 2000s, many believed the broad outlines of the large-scale structure were already known, and that only minor details remained hidden. That confidence turned out to be misplaced. In 2016 and 2017, Renée Krahn-Korteweg and her collaborators used new spectroscopic observations in the zone of avoidance, collecting about 4,500 additional galaxy redshifts from a region that had long been treated as nearly blank. What they uncovered was astonishing: a major supercluster, comparable in scale to the Shapley supercluster, located about 800 million light-years away, and stretching across roughly 320 to 400 million light-years. It had been there all along, hidden behind the Milky Way's dusty plain. They named it the Vela supercluster, after the southern constellation in which it lies. This was not a trivial correction to the map. It was the discovery of one of the largest known structures in the nearby universe, found in a place many had assumed no longer held surprises of that magnitude. published in 2017, the discovery immediately raised a new question. How much has Vela been contributing to our own motion without being included in the earlier models? Current estimates suggest it may add several tens of kilometers per second, but the exact contribution is still being studied. What matters most is the principle. For decades, astronomers had been building models of the Milky Way's motion while missing an entire supercluster hidden in one of the sky's most difficult regions. And Vela may not be the last major structure concealed there. Since 2017, the Meerkat radio array in South Africa has been carrying out blind 2-1 centimeter hydrogen surveys through the zone of avoidance. Because these radio wavelengths pass through galactic dust with very little absorption, Meerkat can see directly into regions that optical telescopes cannot penetrate. The results have been remarkable. In just the early years of operation, the telescope identified hundreds of previously unknown galaxies, many arranged in groups and filaments that hint at even larger structures still awaiting full mapping. These surveys are ongoing, and each new release adds more objects instead of closing the inventory. That pattern is unsettling, because every newly discovered concentration of matter behind the galactic plane is matter that was not fully included in older gravitational reconstructions. The forces guiding the Milky Way may be more complicated than we thought, not because the laws of gravity are wrong, but because our map of the mass distribution is still incomplete. As recently as 2023, the hidden 20% of the sky was still yielding major discoveries. And yet even the zone of avoidance may not represent the deepest uncertainty in this story. That distinction belongs to a much more controversial signal, one that many scientists still debate. In 2008, NASA astrophysicist Alexander Kashlinsky and his collaborators published a claim that deeply unsettled cosmology. They did not report a hidden supercluster or a giant void. Instead, they argued that thousands of galaxy clusters spread across billions of light-years appeared to share a coherent drift in the same direction. They called the phenomenon dark flow. To infer this motion, the team used data from NASA's WMAP satellite and measured the kinematic Sunyaev-Zeldovich effect, in which cosmic microwave background photons passing through the hot gas of galaxy clusters gain a tiny energy shift depending on the cluster's motion. By analyzing this effect across hundreds and then thousands of clusters, they constructed a map of cluster velocities. What they found seemed extraordinary: a large-scale drift of roughly 600 to 1,000 kilometers per second, extending across a region so large that standard cosmology would normally expect motions there to average out into near randomness. If the signal were real, it would imply that structures beyond the observable universe itself were influencing matter within our horizon. That idea was far too radical to be accepted easily. Many researchers challenged the method, questioned the statistics, and argued that instrumental systematics or foreground contamination were more likely explanations. Yet, the claim did not disappear. Kashlinsky's group continued refining the analysis and published follow-up work in 2010 and 2012, keeping the controversy alive. Whether dark flow reflects a genuine cosmic signal or not remains disputed, but the very fact that such a possibility could be entertained reveals how incomplete our understanding still is. We once imagined that our motion through space could be explained by a single hidden attractor. Then we learned it was a broader basin. Then we found a distant supercluster adding to the pull, a giant void contributing from the opposite side, and new hidden structures emerging from behind our own galaxy's dust. The closer astronomers look, the more the universe around us resembles a vast and unfinished map, one in which the Milky Way is not drifting through emptiness at random, but moving through a deep gravitational web whose full shape we are only beginning to see. The signal did not disappear. Each time new analyses were performed, it continued to appear, pointing in roughly the same direction, with a similar strength. The debate surrounding it did not reach a clean resolution, it simply paused, waiting for better data. That data was already on its way. In 2009, the European Space Agency launched the Planck satellite, designed specifically to map the cosmic microwave background with far greater precision than any previous mission. With higher sensitivity, finer resolution, and a wider range of frequency channels, Planck was expected to settle the question once and for all. When its results were released between 2013 and 2016, the conclusion seemed decisive. The Planck team reported no statistically meaningful evidence for the so-called dark flow. Their measurements placed strict upper limits on any large-scale coherent motion, far below the values previously claimed. With improved ability to separate true cosmic signals from foreground contamination, many researchers concluded that the earlier detection had likely been an artifact noise or interference misinterpreted as motion. Within the broader scientific community, this was widely accepted as the final word, yet not everyone agreed. Kashlinsky, who had originally proposed the dark flow, argued that the two analyses were not directly comparable. He pointed out differences in methodology, data selection, and interpretation. In his view, Planck had not disproven the signal so much as failed to detect it under different conditions. The disagreement was never fully resolved. Instead, it faded beneath the weight of consensus, though history has shown that consensus in cosmology is not always permanent. For now, the prevailing view is that dark flow is not an established phenomenon. It is not part of the standard model of the universe, but the question never fully vanished. It lingered quietly in the background, waiting for new data to test it again. And that data arrived in 2023. The fourth release of the Cosmic Flows project, Cosmic Flows 4, presented the largest and most detailed catalogue of galaxy distances ever assembled, containing measurements for nearly 56,000 galaxies. The goal was simple: map how galaxies move relative to the smooth expansion of the universe and compare those motions to theoretical predictions. But the results did not align with expectations. At distances of roughly 500 to 650 million light-years, the data revealed coherent bulk motions, large groups of galaxies drifting together at speeds between 380 and 430 kilometers per second. According to the standard cosmological model, motions at those scales should be closer to 140 kilometers per second. The difference was not subtle. It was roughly 3 times larger than predicted. Statistically, such a discrepancy is extremely unlikely to occur by chance. It falls within a range that scientists take seriously, suggesting either hidden systematic errors or missing pieces in our understanding of cosmic structure. Researchers have proposed both possibilities. Perhaps the distance measurements contain subtle biases that amplify the signal, or perhaps the velocity field at these scales truly behaves in ways our models do not yet capture. There is no agreement yet. The question remains open. At the center of all of this lies a number, 630 kilometers per second. That is the speed at which the Milky Way moves relative to the cosmic microwave background, the oldest light in the universe. This measurement comes from what is known as the CMB dipole. The background radiation appears slightly warmer in the direction we are moving toward, and slightly cooler in the opposite direction. The difference is tiny, but precise enough to reveal both our speed and direction. This result has been confirmed repeatedly over decades. It is one of the most reliable measurements in cosmology. But interpreting what it means is more complicated. There is another way to estimate our motion, by examining how galaxies and quasars are distributed across the sky. Because of our movement, there should be a slight imbalance. More objects in the direction we are heading, fewer behind us. This is called the matter dipole. In theory, it should match the CMB dipole. In practice, it does not. Multiple surveys have found a signal that is roughly twice as large, with a direction that is similar but not identical. The discrepancy is statistically significant and remains unexplained. It raises uncomfortable possibilities. Perhaps the CMB dipole is not purely due to motion. Or perhaps the universe itself is not as uniform in all directions as we assume. Either possibility would challenge fundamental principles of cosmology. For now, both remain unresolved. To understand why these questions matter, we need to step back and look at the structure of the universe itself. On the largest scales, matter is not distributed evenly. It forms a vast network known as the cosmic web. Galaxies gather along enormous filaments, threads of matter stretching hundreds of millions of light years, intersecting at dense nodes where clusters and superclusters form. Between these filaments lie vast voids, regions where matter is scarce. This structure emerged from tiny fluctuations in the early universe, amplified over billions of years by gravity. Most of the matter shaping this web is not visible. Dark matter makes up the majority of it, forming the underlying framework upon which galaxies assemble. What we see, stars, gas, planets, is only a small fraction of the total. The forces guiding our motion are therefore dominated by something we cannot directly observe. The Shapley supercluster pulling us forward, the dipole repeller pushing us away, the Vela supercluster hidden behind our galaxy, all are largely composed of unseen matter. Even Laniakea, our immense gravitational home, is defined by flows shaped primarily by dark matter. This leads to a striking realization. We are moving through a universe we can only partially see, influenced by structures we are still discovering, governed by matter that does not emit light. Our understanding improves with each new observation, but the map is still incomplete. Even our cosmic address has had to be revised repeatedly over time. What once seemed like the full picture, the Virgo supercluster, was later revealed to be just a small part of a much larger structure. In 2014, using galaxy flow data, astronomers redefined that structure and gave it a name, Laniakea. It was not a new place, but a new way of understanding where we have always been. Where galaxy motions all stream toward a shared destination, that region defines a gravitational basin, a kind of cosmic watershed. In that sense, what we once called our home, the Virgo supercluster, is not truly our home at all. It is only a narrow extension, a small branch of something far more immense. Our actual supercluster, as defined by these flows, is Laniakea, a structure spanning roughly 520 million light-years, containing on the order of 100,000 galaxies, and carrying a mass equivalent to about 100 million billion suns. It is nearly 5 times larger than Virgo, and for a brief period, it gave us what felt like a stable cosmic address. But that address did not hold for long. Less than a decade later, new analyses began to challenge even that framework. A study, released in 2024, re-examined the relationship between Laniakea and the far more distant Shapley supercluster. Shapley, located about 650 million light-years away, had always been considered an external influence, a massive neighbor whose gravity helped guide our motion. It was thought to sit beyond us, separate from the structure we belong to. Yet the updated velocity field data suggested something more subtle and more unsettling. There is now a significant probability, around 60%, that Laniakea is not an As-Curie-6 structure at all, but instead a subregion within the larger gravitational domain of Shapley. In this view, what we thought was our own supercluster may actually be part of a greater system, a tributary flowing within a much larger cosmic basin. The result is not yet confirmed. Different methods yield different boundaries, and the question remains open. But if it proves correct, it would mean that the structure we believed we lived inside is itself only a fragment of something larger still. Our cosmic address would need to be rewritten again. This pattern has repeated itself throughout the history of astronomy. Each time we refine our tools, the map expands. Each time we redraw the boundaries, Earth becomes a smaller part of a larger system. The direction of that change has always been the same, outward, towards scales that grow increasingly difficult to comprehend. And at the far edge of what we can observe, there may exist structures that challenge even the assumptions underlying modern cosmology. Everything described so far, Laniakea, Shapley, the dipole repeller, Vela, exists within a relatively small portion of the observable universe. These distances, though immense, still fit within a region that is tiny compared to the full observable cosmos, which extends nearly 46 billion light-years in every direction. At such vast scales, theory makes a clear prediction. The universe should become smooth. Irregularities should average out. Structures larger than about 1 billion light-years should not exist as coherent entities. This idea is known as the cosmological principle, one of the foundations of modern cosmology. And yet, observations have begun to challenge that assumption. In 2013, researchers studying gamma-ray bursts, brief, extremely energetic explosions visible across billions of light-years, identified a possible structure of astonishing size. By analyzing how these bursts cluster across the sky, they found evidence of a region associated with the constellations Hercules and Corona Borealis. The estimated size of this structure, known as the Hercules-Corona Borealis Great Wall, is on the order of 10 billion light-years, across roughly 10% of the entire observable universe. If real, it would be the largest known structure in existence, far exceeding what current theory allows. The result remains debated. Gamma-ray bursts are rare and unevenly distributed, making them difficult to use as precise traces of structure. Some scientists argue that the apparent clustering may be an artifact of incomplete data. Others consider it a serious possibility that demands further investigation. It is not yet confirmed in the same way as structures like Shapley, but it has not been dismissed either. And, if it is real, it would imply that our current understanding of how structure forms in the universe is incomplete. At this point, all the pieces of the story begin to converge. We are a planet orbiting a star within the Milky Way. The Milky Way lies within Laniakea, which may itself be part of the larger Shapley domain. Shapley is embedded within the cosmic web, a vast network shaped largely by dark matter. On one side, we are drawn by massive concentrations of matter. On the other, we are pushed by enormous voids. Meanwhile, regions of the sky remain hidden. Measurements disagree in subtle but persistent ways, and large-scale motions appear stronger than expected. At the greatest distances, even the assumption that the universe is uniform begins to show cracks. For decades, cosmologists relied on a model known as lambda CDM, the standard framework describing how the universe evolves. It has been extraordinarily successful, explaining galaxy formation, large-scale structure, and the cosmic microwave background with remarkable precision. But recent observations have begun to reveal tensions. The bulk flows measured in cosmic flows, 4 are significantly larger than predicted. The mismatch between different dipole measurements remains unresolved. Possible structures exceed theoretical size limits, and older anomalies, like dark flow, continue to resurface in new forms. Each issue on its own might be dismissed. Together, they suggest that the model may be incomplete. This matters because our motion, the fact that the Milky Way is moving at hundreds of kilometers per second towards something we cannot fully see, was supposed to be explained within that framework. If the framework itself is under strain, then the explanation for that motion may also be incomplete. What is pulling us may not be fully accounted for. What is pushing us may not be fully understood. And the deeper we look, the more the answer seems to recede into larger and less familiar territory. Then there is another force entirely, one that changes the ending of the story in a quiet but profound way. In 1998, 2 independent teams studying distant supernovae discovered that the expansion of the universe is not slowing down, as expected, but accelerating. Something is driving space itself apart. That something is called dark energy. It does not emit light, cannot be directly detected, and yet it dominates the universe, making up about 68% of its total energy content. This has a direct consequence for our journey. The Milky Way is moving toward the Great Attractor and influenced by Shapley beyond it. That motion is real. But at the same time, the space between us and those structures is expanding and accelerating. In the long term, that expansion wins. Even as we fall toward these massive regions, they are receding from us. The result is paradoxical but unavoidable. We are moving toward a destination we will never reach. The motion continues forever. The arrival never happens. And even the structures we are moving toward are not permanent. Laniakea itself is not gravitationally bound. It is a pattern of motion, not a lasting structure. Over tens of billions of years, dark energy will stretch it apart. The flows that define it will weaken, then dissolve. What appears today as a coherent region will fragment into isolated systems. Closer to home, some things remain certain. The Milky Way and Andromeda will collide in a few billion years. That event is inevitable because it occurs within a gravitationally bound system, but beyond that local scale, nothing is fixed. The larger structures guiding our motion are temporary, evolving, and ultimately transient. So, we find ourselves in a peculiar situation. Our galaxy is drifting through a vast gravitational landscape, shaped by both matter and emptiness, guided by forces we only partially understand. We are falling towards something that is itself dissolving, across a universe that is expanding faster and faster. The journey has no final destination, only motion without end. He responded not with retreat, but with detailed technical arguments. In a series of follow-up papers written with his collaborator Fernando Atrio Barandella, he maintained that the Planck team had not actually tested the same hypothesis. According to their analysis, the disagreement came down to methodology. The filtering techniques applied to the data were different. The way galaxy clusters were weighted in the calculations was different. In their view, the two teams were not performing equivalent measurements, even though the results were being compared as if they were. They continued refining their approach. When they reapplied their original method carefully, and in their own framework to the Planck dataset itself, they reported that a statistically meaningful dipole signal still appeared. It had not vanished with better instruments. Instead, it shifted depending on how the data was processed. That left the situation in an uneasy state. Both groups were working with real observations. Both followed rigorous procedures, yet they reached incompatible conclusions, and neither side could identify a definitive flaw in the other's work that would settle the issue cleanly. Kashlinsky has since moved toward a new approach. He is developing an experiment designed to test the same underlying question using an entirely different signal, the near-infrared background. This project, known as the Near-Infrared Background Anisotropy and Dipole Experiment, is tied to the European Space Agency's Euclid mission, launched in 2023. Instead of relying on microwave measurements of galaxy clusters, it will examine anisotropies in the infrared background itself. A different wavelength, a different method, but the same fundamental question whether large-scale coherent motion exists beyond what current models can explain. The results have not yet arrived, but when they do, they will carry significant weight. What makes this episode worth reflecting on is not only the result, but the process. Science is often presented as a clean progression from question to answer. In reality, it can look more like this: a prolonged disagreement between careful researchers, each working with valid data, each testing assumptions in slightly different ways. Dark flow has not been confirmed. It has also not been conclusively dismissed. It sits in an uncertain space, technically unresolved, quietly debated, and persistent enough to keep the question alive. For nearly 2 decades, The argument has continued, not as noise, but as a sustained attempt to determine whether something subtle has been overlooked or whether the signal will eventually disappear under better scrutiny. Either outcome would be meaningful. Beyond this debate lies a deeper boundary, one that no instrument can cross. The observable universe extends about 46 billion light-years in every direction. Beyond that limit, the universe continues, but no light or information from those regions has had time to reach us since the beginning of cosmic history. This is not a limitation of technology. It is a fundamental constraint imposed by the age of the universe and the speed of light. If the dark flow signal, or something like it, is real, one of the simplest interpretations is that its source lies beyond that boundary. In models of cosmic inflation, the early universe expanded so rapidly that regions of space now exist far outside our observable horizon. Those regions may contain large concentrations of mass structures formed from primordial fluctuations that we will never directly see. Some versions of inflationary theory allow for such imbalances, suggesting that matter beyond our horizon could, in principle, exert gravitational influence on what we can observe. This idea remains controversial. Some physicists argue that such effects would be untestable and therefore scientifically limited. Others note that current theory does not strictly forbid them. What makes the possibility difficult to ignore is the scale involved. Even within the observable universe, we already encounter structures that stretch the limits of comprehension. Superclusters span hundreds of millions of light-years. Proposed large-scale formations extend across billions. The suggestion behind dark flow is that even larger structures may exist beyond what we can ever measure directly, structures that could subtly influence motion within our visible universe. If that is true, then the Milky Way may be moving under the influence of something it can never observe, guided by physics that can never be fully tested. Even if the original dark flow claim ultimately fades under further analysis, the question it raises does not disappear. Does structure exist beyond the observable universe? Almost certainly, according to inflationary theory. Can that unseen structure affect what happens within our horizon? That remains open. It is a question with a precise mathematical form, but one that may never yield a definitive observational answer. Meanwhile, within the observable universe itself, the data continues to evolve. The Cosmic Flows 4 catalog, released in 2023, provided the most extensive map of galaxy motions to date, covering over 56,000 galaxies out to distances of roughly 600 million light-years. When researchers analyzed the collective motion of galaxies within that volume, they found a coherent flow in the range of 380 to 430 kilometers per second, aligned with earlier indications of motion toward the Shapley region. Within its own uncertainties, the result was statistically robust. Yet, it remained larger than what the standard cosmological model predicts. Under lambda CDM, such large-scale flows should be significantly smaller. The probability of observing a flow of that magnitude purely by chance within the model is extremely low, on the order of 1 in hundreds of thousands. That is not the kind of result scientists dismiss lightly. It demands explanation.
Even at the
In 2026,
speed of light.
a reanalysis of the same dataset attempted to account for a known issue: uneven survey coverage across the sky. Because observations are denser in some regions than others, this anisotropy can introduce artificial signals. After applying corrections, the estimated bulk flow dropped substantially, in some interpretations to around 75 to 80 kilometers per second. At first glance, this seemed to resolve the discrepancy, but it did not fully eliminate it. Even after correction, a measurable tension remained between observation and prediction. This pattern has appeared repeatedly. Each time the data is refined, the anomaly becomes smaller, but it does not vanish. A residual persists. That persistence leaves two possibilities. One is that the signal reflects a real physical effect, partially obscured by measurement challenges. The other is that it arises from subtle, systematic errors that have not yet been fully identified. Both interpretations are taken seriously. Both remain plausible. What is clear is that the motion of the Milky Way is not just a local curiosity, it is a probe of the universe itself. Because gravity cannot be observed directly, astronomers infer the distribution of mass by tracking how galaxies move. Our galaxy's velocity encodes the cumulative influence of every significant mass concentration within reach across cosmic history. The slight temperature asymmetry in the cosmic microwave background, the dipole, tells us both our speed and our direction. Everything else in this story is an attempt to explain why that number has the value it does. If the motion we measure does not align perfectly with theoretical expectations, then either the distribution of matter is not what we think it is, or the theory itself is incomplete. That is why peculiar velocity surveys have become precision tools for testing cosmology. Each new dataset is not just a map, it is a test of whether our understanding holds. And the next wave of data is already underway. Instruments like the Dark Energy Spectroscopic Instrument, the Vera Rubin Observatory's Legacy Survey of Space and Time, and the Euclid mission are expanding the reach and precision of these measurements. Over the coming years, they will map the universe in unprecedented detail. When those maps are complete, the outcome will move in one of two directions. Either the anomalies will shrink, aligning observations more closely with the standard model, or they will persist and deepen, pointing toward new physics. One outcome reinforces what we believe we know. The other forces us to rethink it. Both are valuable, and both are approaching quickly as the instruments continue their quiet work, gathering data that will shape how we understand our motion through the universe. When these next-generation surveys are complete, they will transform what is currently a fragmented picture into something far more precise. The Dark Energy Spectroscopic Instrument, for example, is expected to measure the redshifts of around 40 million galaxies and quasars, tracing more than 11 billion years of cosmic history. From those measurements, astronomers will extract peculiar velocities and map large-scale flows with a level of detail that has never before been possible. Earlier catalogues worked with thousands of galaxies. This one works with millions. What once were sparse samples will become dense, continuous fields. What once were partial maps will approach something closer to completeness. At the same time, on the ground in Chile, the Vera C. Rubin Observatory is beginning its long-term survey of the southern sky. Over the course of a decade, it will repeatedly image vast regions of space, generating a dataset measured not in gigabytes or terabytes, but in petabytes. Among its many objectives is the discovery of hundreds of thousands of Type Ia supernovae, the same kind of stellar explosions that first revealed the accelerating expansion of the universe. Each of those events provides a distance measurement. Each distance contributes to the reconstruction of galaxy motions. Where previous studies relied on hundreds of such measurements, Rubin will provide them in the hundreds of thousands. In orbit, the Euclid satellite is already extending this effort further. Launched in 2023, it is mapping the shapes and positions of billions of galaxies across 10 billion years of cosmic time. Its measurements of weak gravitational lensing will reveal how matter, both visible and invisible, is distributed across enormous scales. Unlike ground-based surveys, it operates free from atmospheric distortion, offering a level of precision that complements and strengthens everything measured from Earth. It will also host the instrument designed to test the dark flow hypothesis using near-infrared observations, providing an entirely independent line of evidence. Meanwhile, in South Africa, the Meerkat Radio Array continues to explore regions of the sky that have long remained hidden. The dense band of dust in the Milky Way blocks optical observations of everything lying behind it. leaving a substantial portion of the universe poorly mapped. Radio waves, however, pass through that dust with little resistance. Meerkat is using this advantage to catalogue galaxies within the so-called zone of avoidance, gradually filling in gaps that have persisted for decades. With each new detection, the gravitational map becomes more complete. Within the next 10 years, the data from all these instruments will begin to overlap. The anomalies identified in earlier studies will be tested against vastly larger and more precise datasets. The apparent mismatch in bulk flows will either diminish or become more pronounced. The tension between different measurements of cosmic motion will be examined with unprecedented clarity. The hidden regions behind our galaxy will be revealed in detail, and the long-standing question of convergence, whether all the mass influencing our motion can be fully accounted for within a finite distance, will finally face a decisive test. If everything aligns, the picture may settle. The remaining discrepancies could fade as measurement errors are corrected and previously unseen structures are incorporated into the models. The standard framework would hold, strengthened by deeper and more comprehensive data. But if the discrepancies persist, if, even with this level of precision, the numbers still refuse to close, then the problem will no longer be attributed to measurement. It will point instead to a gap in the theory itself. At present, we already know more about our motion through the universe than any previous generation. The Milky Way is moving at roughly 600 kilometers per second relative to the cosmic microwave background. That value has been confirmed repeatedly. Its direction toward the region of the Centaurus constellation and beyond toward the Shapley concentration has remained stable across decades of observation. We understand that our galaxy lies within a vast gravitational basin, hundreds of millions of light-years across, and that its motion is shaped both by attraction toward dense regions and by repulsion from immense voids behind us. We also understand something more subtle and more unsettling. We will never arrive at the destination toward which we are moving. The expansion of the universe, driven by dark energy, ensures that the structures we are falling toward are receding at the same time. The motion continues, but the endpoint retreats indefinitely. The journey has direction, but no final arrival. And yet, despite all that we have learned, the model that describes this motion is not perfectly secure. The large-scale flows are still somewhat stronger than predicted. Different methods of measuring our motion do not align perfectly. The distribution of matter, especially in regions hidden from direct observation, is still incomplete. Each refinement reduces the uncertainty, but does not eliminate it. A small remainder persists, and that remainder refuses to vanish in the way simple measurement errors typically do. There are still blank regions on the map. Structures behind the plane of our own galaxy are only now being revealed. There are depths beyond current surveys where additional influences may still be found. There are hypotheses like dark flow that remain unresolved, waiting for new instruments to test them from entirely different angles. And there will be future anomalies, emerging from data that has not yet been fully analyzed, from patterns that do not quite fit within the expectations of the current model. The history of this field has always followed that pattern. Each generation builds better instruments. Each instrument produces more detailed maps. Each map resolves some questions and raises new ones. The process does not end with certainty. It continues, refining, correcting, expanding. And right now, as these new surveys quietly collect their data, the next revision of our understanding is already forming. The next survey is already collecting its data. Somewhere, in a dataset not yet fully analyzed, there is a pattern that does not quite fit, a direction that is slightly off, a velocity that is slightly too large, a structure that is slightly too big. At first, it will look like noise, like all anomalies do. It will be checked, corrected, recalculated. Most of the time, those signals disappear under scrutiny. Sometimes, they do not. This is how the map changes, not all at once, but in increments. A correction here, a new structure there, a refinement of a number that shifts everything else by a small but meaningful amount. Over time, those small shifts accumulate until the picture itself has to be redrawn. And when it is redrawn, the scale expands again. The center moves again. The address changes again. We have already seen this pattern. Earth was once the center, then it became one planet among many, then one system among billions, then one galaxy inside a cluster, then a cluster inside a supercluster, then a supercluster inside a basin. And now even that basin may be part of something larger still. There is no indication that this process is finished. Every improvement in measurement has moved the boundary outward. Every increase in precision has revealed more structure beyond what we thought was the edge. What makes the present moment different is not just the scale of the instruments, but the density of the data. For the first time, astronomers are approaching a point where the velocity field of the nearby universe can be mapped continuously rather than sampled sparsely. Instead of isolated measurements, there will be full three-dimensional flows. Instead of approximations, detailed reconstructions. That level of detail removes excuses. If something does not match the model at that precision, it cannot easily be attributed to missing data. And so the question becomes sharper, not just what is pulling us, but whether everything that should be pulling us has already been accounted for. Not just where we are going, but whether the framework used to describe that motion is complete. There is a quiet tension in that question, because the standard model of cosmology has been extraordinarily successful. It explains the cosmic microwave background, the formation of galaxies, the large-scale distribution of matter. It has passed test after test, but success does not guarantee completeness. And the places where it struggles, subtle mismatches, persistent residuals, structures that seem too large, or motions that seem too fast, are precisely where new physics tends to emerge. If the upcoming surveys confirm the current model, then the story settles. The remaining discrepancies will shrink. The motion of the Milky Way will be fully explained by known structures, known forces, known equations. The universe will become, in some sense, more predictable, more complete. But if they do not, if the anomalies remain, or grow stronger, then the story changes. It becomes a story not of refinement, but of revision. The forces shaping our motion may not be fully described by the current framework. The structures influencing us may extend beyond what we have mapped. The assumptions about uniformity at the largest scales may need to be reconsidered. And in that case, the simple statement that began this investigation takes on a different weight. Earth is moving through space. That much is certain. It is moving towards something. That much is measured. But what that something is, how far it extends, how it is structured, whether it is fully visible or only partially known, remains an open question. We are carried along by gravity, shaped by both mass and emptiness, guided by a landscape we are still in the process of discovering. The motion feels smooth, constant, almost invisible from our perspective. But on the largest scales, it is part of a vast and evolving pattern, one that stretches across distances that resist intuition. And beyond the edge of what we can see, beyond the limit where light has had time to reach us, the universe continues. Whether anything there influences us is not something we can confirm directly. But the possibility remains, written into the equations, suggested by hints in the data, waiting for either confirmation or dismissal. For now, we exist in the middle of that uncertainty, not at rest, not at a destination, but in motion, steady, continuous, and guided by forces that are only partially understood. The universe does not provide a fixed point to arrive at. It provides a direction, a velocity, and a horizon that keeps moving. And somewhere ahead, hidden within that motion, is the answer we have not yet fully uncovered. If we step back and look at everything that has been measured so far, a pattern begins to emerge, not a complete answer, but a set of constraints that any explanation must satisfy. The Milky Way is moving at approximately 630 kilometers per second relative to the cosmic microwave background. That number is one of the most precise in cosmology, derived from the temperature dipole of the CMB and confirmed across multiple missions, from COBE to WMAP to Planck. The direction is equally well established, pointing toward the Centaurus Hydra region, roughly aligned with the Great Attractor, 250 million light-years away, and extending further toward the Shapley supercluster to 650 million light-years away. But when we try to reconstruct the cause of that motion using known mass distributions, the accounting does not close cleanly. The Great Attractor region, centered near the Norma cluster, contributes significantly, but its estimated mass, on the order of 10 to the power of 15 solar masses, is not sufficient to explain the full velocity. The Shapley supercluster, much farther away but vastly more massive, at roughly 5 times 10 to the power of 16 solar masses, adds a comparable contribution, despite its distance. Together, they explain a large fraction of the motion, but not all of it. Then there is the dipole repeller, a void extending roughly 700 million light-years in the opposite direction. Its contribution is not from mass, but from the lack of it. Simulations and reconstructions suggest that this underdense region contributes a non-negligible fraction of our velocity, possibly comparable in magnitude to Shapley's pull. Even after including all 3 components, Great Attractor, Shapley, and the dipole repeller, a residual remains. That residual shows up in multiple ways. In cosmic flows, for 2023, the measured bulk flow at scales of 150-200 meters parks is approximately equal to 500-650 million light-years, lies in the range of 380-430 kilometers per second, while the Lambda CDM model predicts values closer to 140 kilometers per second. Even after corrections for survey anisotropy, reducing the estimate to 75-80 kilometers per second, the discrepancy does not vanish entirely. At the same time, the matter dipole derived from galaxy and quasar distributions appears to be roughly twice as large as the CMB dipole, with a statistical tension in the 3-5 sigma range, depending on the dataset. These are not isolated anomalies. They are different measurements of the same underlying phenomenon, motion through the large-scale structure of the universe. So what could explain them? One possibility is the most conservative: incomplete mapping of mass. We know that roughly 20% of the sky lies behind the Milky Way's disk, the zone of avoidance. Surveys like Meerkat are beginning to fill in that region, revealing previously unknown galaxies and even major structures like the Vela supercluster to 800 million light-years away, hundreds of millions of light-years across. If additional mass concentrations exist there, they could alter the gravitational balance enough to reduce the discrepancy. A second hypothesis is that convergence depth has not yet been reached. Early estimates suggested that the sources of our motion should lie within 150 million light-years. Later work pushed that to 300 million, then to 600 million, and now possibly beyond. If significant contributions continue to arise from structures at is greater than 1 billion light-years, then current surveys may simply not extend far enough to capture the full gravitational field. A third possibility involves large-scale anisotropy, a violation, or at least a weakening, of the cosmological principle. If the universe is not perfectly uniform at the largest scales, then coherent flows larger than expected could arise naturally. Structures like the proposed Hercules Corona Borealis Great Wall, to 10 billion light-years across, if confirmed, would directly challenge the assumption that matter distribution smooths out beyond 1 billion light-years. A fourth hypothesis returns to the most controversial idea, dark flow. If there exists a coherent motion extending across billions of light-years, with velocities on the order of 601,000 kilometers per second as originally claimed, then local structures alone cannot explain it. The simplest explanation in that framework is gravitational influence from mass concentrations beyond the observable universe. Inflationary cosmology allows for this possibility. During the earliest moments of the universe, space expanded exponentially, potentially placing large-scale density variations beyond our horizon. If such regions exist, and if they are sufficiently massive and close to the boundary of observability, they could imprint a preferred direction on structures within our visible universe. This idea is not confirmed. It may never be testable in a direct sense, but it remains mathematically consistent within certain models. A fifth possibility is more radical: new physics at large scales. Lambda CDM assumes that gravity behaves according to general relativity across all scales, and that dark matter and dark energy account for all major effects. But if deviations exist, whether in the behavior of gravity, the distribution of dark matter, or the properties of dark energy, then large-scale motions could differ from predictions. For example, if dark energy is not perfectly uniform, it could introduce directional effects. If dark matter clusters differently at very large scales, it could alter flow patterns. If gravity itself behaves differently over hundreds of millions of light-years, the entire framework would need revision. None of these ideas are confirmed. All of them are under investigation. What is clear is this: every measurement we make of the Milky Way's motion is also a measurement of the universe's structure. The velocity of our galaxy, its magnitude, its direction, its deviations from prediction, is a direct probe of how matter is distributed across vast distances. And right now, that probe is giving answers that are close to what we expect, but not perfectly aligned. Close enough to trust the model, not close enough to stop questioning it. So we are left in a state that is scientifically familiar, but conceptually unsettling. We know the speed, to 630 kilometers per second. We know the direction, toward Centaurus, Shapley, and beyond. We know many of the contributors, massive clusters, vast voids, hidden structures. But we do not yet know if we have found all of them. And until the accounting fully closes, until every contribution is measured, every anomaly explained, the possibility remains that part of what is guiding our motion lies beyond what we can currently see, or even beyond what we can ever observe. And once you begin to follow that line of reasoning, the question stops being about a single destination and becomes something far larger, something far more difficult to contain within a simple explanation. Every time cosmology has tried to close the system, something has remained just slightly out of place. The numbers nearly align, the models nearly hold, the maps nearly feel complete, but not entirely. Consider the idea of convergence depth. In theory, there should be a distance beyond which adding more data no longer changes the result, a boundary where all relevant mass has been accounted for and the gravitational calculation stabilizes. Yet that boundary has never stayed fixed. It has steadily moved outward as measurements improved, first around 100 million light-years, then 300 million, then 600 million, and now possibly approaching or exceeding 1 billion light-years. Each time the horizon expands, the answer shifts again. That is not the behavior of a closed system. It is the behavior of something that keeps extending beyond where we expect it to end. At the same time, the direction of our motion has remained remarkably stable. Across decades of independent observations, from the cosmic microwave background dipole to galaxy surveys and velocity catalogues, the Milky Way continues to move toward roughly the same region of the sky. That consistency suggests we are not dealing with random fluctuations. Yet the magnitude of that motion refuses to settle cleanly. Different methods yield slightly different speeds. The matter dipole appears larger than the CMB dipole, and large-scale bulk flows persist above theoretical expectations. This does not point to randomness, it points to missing structure. Then there is the zone of avoidance, a region covering roughly 20% of the sky, long obscured by the dust and gas of our own galaxy. For decades, cosmologists have been solving the gravitational equation of our motion while missing a significant portion of the data. Only recently have radio surveys begun to reveal what lies behind that veil. The discovery of the Vela supercluster alone demonstrated that entire massive structures could remain hidden in regions once considered observationally incomplete but dynamically unimportant. That assumption no longer holds. And as instruments like Meerkat continue to map these regions, they are not uncovering isolated objects, but patterns, filaments, clusters, and groupings that hint at even larger structures still unresolved. Each addition subtly reshapes the gravitational landscape, and the pattern repeats. There is always more mass than we had accounted for, yet at the same time, there is also less. The dipole repeller represents not a concentration of matter, but a deficit, a vast void extending hundreds of millions of light years. And still, it contributes to motion. This is where intuition begins to fail, because we are not only being pulled by what exists, but also influenced by what does not. Gravity at these scales operates through gradients, through differences between dense and empty regions. The universe is not a uniform field with isolated objects scattered within it. It is a terrain of peaks and valleys, and we are moving through that terrain along slopes we cannot directly see, drifting away from depths we cannot fully map. Now place this into the context of dark energy. At smaller scales, gravity dominates and structures form, pulling matter inward. But beyond a certain scale, dark energy drives accelerated expansion, stretching space itself. The result is that the very structures influencing our motion today are not permanent. They exist within a temporary balance between attraction and expansion. Over billions of years, that balance shifts. Superclusters fragment, flows weaken, and galaxies become increasingly isolated. The motion we measure now, this steady drift of roughly 600 kilometers per second, is a snapshot of a transient configuration, not a final state. And beyond all of this lies the observable limit of the universe itself. Everything we have mapped exists within a finite region defined by how far light has traveled since the beginning of cosmic time. Beyond that boundary, the universe continues, but we cannot see it, measure it, or directly test it. Yet if mass exists just beyond that horizon close enough, large enough, it could still influence motion within the observable region. Not in a way we can image, but in a way that might appear as exactly what we already observe. A persistent residual, a slight mismatch, a direction that remains consistent while its explanation remains incomplete. This possibility does not need to be confirmed directly to remain relevant. It only needs to account for what current models fail to fully explain. And right now, they do not fully explain it. Not dramatically, not in a way that breaks the entire framework, but in a way that refuses to vanish under refinement. Even within the observable universe, most of the matter shaping these motions is invisible. Dark matter, which makes up the majority of the mass in large-scale structures, does not emit or absorb light. It is inferred through gravitational effects, not directly observed. That means even our best maps are reconstructions, built from motion rather than direct detection. We are tracing the outline of something we cannot fully see, solving for a structure whose dominant component remains hidden. And still, the model works almost. That is what makes it compelling. If it failed entirely, it would be easy to discard. If it matched perfectly, there would be nothing left to investigate. But it sits in between, accurate enough to trust, incomplete enough to question. And so the investigation continues, not because we lack knowledge, but because we have reached the edge of what that knowledge can currently resolve. Each new instrument extends that edge further outward. Each new dataset fills in part of the map, only to reveal that the boundary itself has shifted again. The question is no longer simply what is pulling the Milky Way, but how far that influence extends, how deep the structure runs, and whether there is any true boundary at all where the explanation finally comes to rest. And if that boundary does not exist, if the explanation never fully closes, then the nature of the problem changes entirely. Because up to this point, the assumption has always been that the universe is, at some scale, self-contained in its explanation. That if we map far enough, measure precisely enough, and account for all the mass within reach, the motion of the Milky Way will resolve into a complete and stable answer. That there is a depth at which the gravitational bookkeeping balances perfectly. But what if that depth keeps moving because the system itself is not closed in the way we assume? There is a subtle but important distinction here. A closed system is one where all influences can, in principle, be measured and accounted for within a finite boundary. An open system is one where influences extend beyond any boundary you can define. The observable universe gives us a natural limit, but it does not guarantee that all relevant causes lie within it. This is where the convergence problem becomes more than just a technical issue. If every increase in survey depth reveals new contributors, new mass, new voids, new gradients, then the idea of a final accounting begins to lose its footing. The question shifts from, how far do we need to look, to, is there a distance that is enough at all? And that question connects directly to the behavior of large-scale flows. Because the expectation under the standard model is clear, as you average over larger and larger volumes, the universe should smooth out. Local irregularities should cancel. Coherent motion should diminish. At sufficiently large scales, everything should look statistically uniform. But the measurements do not fully follow that expectation. Even when surveys extend to hundreds of millions of light-years, coherent motion remains. Even after corrections, even after accounting for known structures, there is still alignment, still directionality, still a preferred flow. Not overwhelmingly large, not enough to overturn the model outright, but enough to resist being averaged away. Now consider what that implies for the cosmic web itself. We often describe it as a network of filaments and nodes, with matter flowing along these structures toward dense regions. But that description carries an assumption that the web is finite in its effective influence, that beyond some scale its structure no longer organizes motion in a coherent way. But what if the web is deeper than that? What if the filaments extend further than we have mapped? What if the nodes we identify Shapley, Norma, Vela are not endpoints, but intersections within a much larger network? In that case, what we call a supercluster may not be a final structure at all. It may be a local feature within a hierarchy that continues upward in scale. And if that hierarchy continues, then the motion we measure locally is not determined by a single dominant attractor, or even a small set of them, but by a chain of influences extending across scales we have not yet fully accessed. There is also another layer to this that is easy to overlook. All of these measurements, velocities, redshifts, distributions, are taken within a framework that assumes the laws of physics are the same everywhere and everywhen at large scales. That assumption has been extraordinarily successful, but it is still an assumption. If there are subtle deviations, if gravity behaves slightly differently over billions of light years, or if dark energy is not perfectly uniform, then the patterns we observe could reflect not just unseen structure, but incomplete laws. For example, if dark energy varies even slightly across space, it could introduce directional biases in expansion. If the properties of dark matter change at large scales, it could alter how structures form and how strongly they pull. If gravity itself has corrections at very low accelerations or very large distances, then the entire velocity field could shift in ways that current models do not capture. None of these possibilities are confirmed, but none of them are ruled out. And then there is time. Everything we observe is not happening now in a universal sense. When we look at a galaxy 500 million light-years away, we see it as it was 500 million years ago. When we map structures across billions of light-years, we are stitching together a picture that spans vast stretches of cosmic history. Which means the gravitational field we are reconstructing is not a snapshot, it is a composite. Different parts of the map correspond to different moments in time. The structures pulling us today are not exactly the same as the structures we observe at those distances. They have evolved, merged, shifted, changed their mass distributions. So when we ask what is pulling the Milky Way, we are implicitly asking a time-dependent question. Not just what is out there, but what was out there when the signal we now observe began influencing us. That adds another layer of uncertainty. Because even if we map everything perfectly as it appears today, we are still reconstructing a past configuration that may not match exactly what we see. All of this leads to a picture that is both precise and incomplete. We know the motion exists. We know its speed. We know its direction. We know many of its contributors. But the full chain of causation, the complete set of influences across all relevant scales, remains just out of reach. And each time we extend that reach, the answer becomes clearer, and at the same time, more expansive. So the investigation does not narrow. It widens, not because we are failing to understand, but because the system we are trying to understand may be larger, deeper, and more interconnected than the frameworks we started with were designed to handle. And that leaves us with a situation that is both grounded in data and open in interpretation. We are not guessing, we are measuring. But what we are measuring is a motion that seems to connect local structure, large-scale organization, hidden regions of the sky, and possibly even influences that extend beyond what we can ever directly observe. Which brings the question back, in a slightly different form. Not just what are we moving toward, but how many layers of structure are involved in determining that motion? Whether, at the largest scales, those layers ever truly come to an end. We know, with high precision, that the Milky Way's velocity relative to the CMB rest frame is to 627 plus or minus 22 kilometers per second, a value confirmed across multiple missions including COBE, WMAP, and Planck. The dipole, anisotropy in the cosmic microwave background, on the order of 2-3. 36 millikelvin difference across the sky encodes that motion with extraordinary reliability. This is not a disputed measurement. It is one of the most stable anchors in all of cosmology. We also know that when we break that motion down into contributions, the numbers do not collapse into a single dominant source. The Virgo cluster, at roughly 1620 mpc to 5065 million light-years, contributes a local infall velocity of about to 250 kilometers per second. That is well measured through galaxy distance indicators and peculiar velocity surveys. The Great Attractor region, centered near the Norma cluster, at approximately to 60-70 mpc to 230 million light-years, adds a larger scale component. Estimates vary depending on methodology, but its contribution is typically modeled in the range of to 300-400 kilometers per second when combined with surrounding structures. Then further out, the Shapley supercluster, located at roughly to 200 mpc to 650 million light-years, contributes an additional component estimated at 5100 kilometers per second, despite its distance, due to its enormous mass on the order of several times 10 to the power of 16 solar masses, making it one of the most massive known structures in the nearby universe. Even when these are combined, the vector sum approaches but does not perfectly reproduce the observed to 600 plus km motion. And that gap is where the tension lives. Now consider the bulk flow measurements. The cosmic flows, 3 dataset, 2016, which included about 18,000 galaxy distances, found bulk flows on scales of 200 mpc, consistent with amplitudes around 200 and 5,300 kilometers per second. This was already somewhat higher than the simplest lambda CDM expectations, but still within tolerable statistical bounds. Then cosmic flows 2023 expanded the dataset to 55,000 plus galaxies, and the measured bulk flow increased to approximately 380-430 kilometers per second at similar scales. Under the standard cosmological model, LCDM, the expected bulk flow amplitude at those scales is closer to 100-150 kilometers per second. That is a factor of roughly 2.5 to 3 times higher than predicted. Statistically, depending on the exact scale and analysis, this corresponds to probabilities on the order of 10 to the power of -5 to 10 to the power of -6, meaning such a result would occur by chance less than once in hundreds of thousands of realizations under the standard model. That is not definitive evidence of new physics, but it is not comfortably ignorable either. Then there is the dipole inconsistency. The CMB dipole gives us to 630 kilometers per second, but independent measurements using radio galaxy catalogs such as NVSS, NRAO, VLA Sky Survey, and more recent quasar catalogs like CatWise 2020, 2022 find a matter dipole amplitude roughly 1.5-2 times larger than expected. In some analyses, this corresponds to effective velocities exceeding to 1,000 kilometers per second, with discrepancies at the 3-5 sigma level. Again, not enough to declare a breakdown, but enough to prevent closure. And then we return to structure. The Laniakea supercluster, defined in 2014 using cosmic flows, 2 data, spans roughly to 160 mpc to 520 million light-years and contains on the order of 10 to the power of 17 solar masses. It is defined not by density alone, but by flow coherence, galaxies whose peculiar velocities converge toward a shared basin. But even that definition is now under question. Recent analyses, 2024, suggest that Laniakea may not be an AS2S, AS-UL, but rather part of a larger flow system connected to Shapley, with a 60% probability depending on reconstruction method, which implies that what we call a supercluster may not be a final unit. It may be a scale-dependent feature. Then there are voids. The dipole repeller, identified through Wiener filter reconstructions, lies roughly opposite the great attractor direction and extends across to 250 mpc, 700-800 million light-years. Its contribution is not through attraction, but through underdensity, a region where the gravitational pull is weaker than average, causing matter to flow away from it. Simulations and reconstructions suggest that this repulsive contribution is comparable in magnitude to major attractors. So the Milky Way's motion is not a single pull. It is a vector sum of local infall to 200 kilometers per second, intermediate attractors to 300-400 kilometers per second, distant superclusters to 5,100 kilometers per second, void-driven gradients, comparable contributions. And still, a small mismatch remains. Now layer in dark energy. At scales beyond to 1-2 GPC, the expansion of the universe accelerates due to dark energy, which accounts for roughly 68-69% of the total energy density of the universe. Planck 2018 results. This acceleration means that large-scale structures are not static targets. They are receding. Even as we move toward Shapley at hundreds of kilometers, the metric expansion of space causes it to recede at thousands of kilometers, depending on distance. So in moving coordinates, we are falling. In physical coordinates, the target is moving away. This is not speculation. It is a direct consequence of the Friedmann equations governing cosmic expansion. So we arrive at a system defined by numbers that are all individually well measured. To 630 kilometers per second, total motion. To 200 kilometers per second, local contribution. To 400 kilometers per second, intermediate structures. To 5100 kilometers per second, distant mass. Residual discrepancies at tens to hundreds of km. Bulk flows exceeding predictions by factors of 2 to 3. Dipole mismatches at 3-5 sigma. Each number is real. Each comes from independent datasets, and none of them, on their own, breaks the model. But together, they form a pattern that does not fully settle. So the possibilities remain open, but constrained. It could still be incomplete mass mapping hidden structures, especially in the zone of avoidance or at greater depths. It could be statistical and systematic uncertainties, distance measurements, survey geometry, selection bias. It could be large-scale anisotropy, a deviation from perfect uniformity at scales where LCDM assumes smoothness. It could be new physics modifications to gravity, dark matter behavior, or dark energy properties at very large scales. Or, in the most extreme interpretation, it could involve influences near or beyond the observable horizon, though this remains speculative and unconfirmed. And the critical point is this: we are no longer in a regime where we lack data. We are in a regime where the data is beginning to outpace the simplicity of the models. Within the next decade, surveys like DESI, 40 million redshifts, Euclid, billions of galaxies, and Rubin Observatory, hundreds of thousands of supernovae, will reduce uncertainties dramatically. If the discrepancies shrink, the model survives stronger. If they persist at high precision, the explanation will have to expand. And that is where the tension becomes most interesting. Because for the first time, the question is no longer whether we can measure our motion. We already can. The question is whether the universe, at its largest scales, is exactly as simple as we assumed when we first wrote down the equations, or whether something small in magnitude but persistent across datasets is pointing towards structure, physics, or influence that we have not yet fully accounted for. Everything we have described so far, velocities, attractors, voids, dipoles, exists inside a framework that assumes the universe is, at large scales, understandable through accumulation. Add enough data, map enough structure, and the picture should resolve. But what if the limitation is not how much we have measured, but how we are thinking about what we measure? Consider this. Every number we use to describe motion, 630 kilometers per second, 400 kilometers per second, 100 kilometers per second, is not a direct observation of cause. It is an observation of response. We are not measuring gravity itself. We are measuring how matter reacts to it. The entire reconstruction of the cosmic landscape is built from motion, not from direct detection of the underlying field. That means we are always working one step removed from the source. Now imagine trying to reconstruct the shape of an ocean by watching only the paths of drifting objects on its surface. You can infer currents. You can map flows. You can identify convergences and divergences. But you are not directly seeing the forces beneath. You are building a model of them. And that model works remarkably well, but only up to the precision of the patterns you can observe. So the question becomes, when the patterns do not fully align, is it because the ocean is more complex than expected, or because the way we are interpreting the drift is incomplete? There is another layer here that invites a deeper kind of thinking. All of our measurements depend on light. Every galaxy we map, every redshift we calculate, every structure we identify, these are all derived from electromagnetic signals. Even when we move beyond visible light, into radio or infrared, we are still relying on radiation that travels through space and reaches our instruments. But gravity does not need light. It operates regardless of visibility, regardless of whether a region emits or absorbs radiation. That is why dark matter could dominate the structure of the universe while remaining invisible. It is also why a region could, in principle, influence motion without leaving a clear electromagnetic signature. So when we say we have mapped the universe, what we really mean is that we have mapped the part of the universe that interacts with light in ways we can detect. That distinction matters, because it leaves open the possibility that the gravitational landscape is more complex than the luminous one. Now take that one step further. If most of the matter in the universe is dark, roughly 85% of the total matter content, and if dark energy dominates the overall dynamics at large scales, then the visible universe is not just incomplete. It is a minority component, which means the structures we see, galaxies, clusters, superclusters, are traces, not the primary framework. They outline something deeper, something largely unseen. So when we observe motion that does not perfectly match our expectations, we are not just questioning where galaxies are, we are questioning how the unseen majority is distributed. And that leads to a different kind of question entirely. Not what is pulling us, but how much of what is pulling us is fundamentally invisible to the methods we rely on. Because if even a small fraction of the gravitational field is shaped by structures that do not correlate cleanly with luminous matter, then mapping galaxies alone will never fully resolve the motion. The mismatch would not disappear with better telescopes. It would persist because the underlying cause is not fully represented in the data we are collecting. There is also the question of scale itself. Human intuition is built around local systems, planets, stars, galaxies. Even clusters and superclusters stretch that intuition, but they remain conceptually manageable, collections of objects bound or connected in some way. But once you move into scales of hundreds of millions or billions of light years, the concept of a structure becomes less clear. What defines a boundary at that scale? Is a supercluster a physical object, or is it simply a region where motion happens to converge under current conditions? If the latter is true, then structures like Laniakea are not fixed entities. They are patterns in motion, temporary configurations defined by flow, not by permanent binding. And if structures are defined by flow, then changing the scale of observation changes the structure itself. Zoom out far enough, and what looked like a distinct basin may dissolve into a larger one, which is exactly what recent analyses suggest might be happening with Laniakea and Shapley. That idea challenges something subtle but important. It suggests that the universe may not be organized into neatly nested, discrete levels, galaxy, cluster, supercluster, and so on, but rather into a continuous hierarchy where each level blends into the next. In that kind of system, asking, "Where do we belong?" becomes less about finding a fixed address and more about choosing a scale of description. At one scale, we are in the local group. At another, in Laniakea. At another, possibly within a larger Shapley-connected flow. And beyond that, the structure may continue, without a clear boundary where it stops. There is also a temporal dimension that complicates everything further. The structures we observe are not static. They evolve over time. Clusters merge, filaments stretch, voids expand. The gravitational field itself changes as matter redistributes. But our observations are not synchronized. When we look at different distances, we are looking at different times. So the map we build is not a snapshot of a single moment. It is a layered reconstruction across billions of years. Which means the structure influencing us today is not exactly the same as the structure we observe at those distances. We are inferring present influence from past configurations. That works because gravity propagates at the speed of light, but it introduces subtle complexities when trying to match cause and effect across time. And then there is the most difficult question to hold in mind. If the observable universe is finite, not in size, but in what we can access, then any explanation based solely on what lies within it is, by definition, incomplete in a larger context. We can build a self-consistent model within that boundary. We can test it, refine it, confirm it to high precision, but we cannot guarantee that all relevant influences are contained within it, because we cannot see beyond it. So the situation we arrive at is not one of ignorance, but of layered understanding. We know the motion exists. We know its scale. We know many of the contributors. We know the framework that explains most of it. But we also know that the explanation is not perfectly closed. And that gap, small in magnitude, but persistent across independent measurements, is where the deeper questions begin. Not because something is obviously wrong, but because something is not yet fully complete. And that is what makes this problem so compelling. It sits at the edge of what we can measure and what we can infer. It is grounded in data, but open in interpretation. It connects local motion to the largest structures in the universe, and possibly to regions beyond what we can ever directly observe. And it asks, quietly but persistently, when you follow motion all the way to its source, do you eventually arrive at an answer? Or do you arrive at a boundary where the question itself has to change? What makes this motion stranger than it first appears is that the best verified part of the story is also the part that refuses to stay simple. The cosmic microwave background dipole is measured so well that it serves as one of the firmest reference points in modern cosmology. Planck-era analyses recover a solar system barycenter motion of about 369 kilometers per second relative to the CMB, encoded in the sky's strongest large-scale temperature asymmetry, and the broader local group motion inferred from the same framework is the familiar roughly 600 kilometers per second scale that anchors this entire problem. That is why astronomers do not debate whether we are moving in a preferred direction through the nearby universe. They debate what combination of structures is producing that motion and whether the known structures are enough. The first major revision came when peculiar velocity mapping stopped treating our environment as just the Virgo supercluster and instead identified a much larger flow basin. The 2014 Nature paper defining Laniakea described a coherent watershed about 160 mpc, or roughly 520 million light-years, across, enclosing about 100,000 galaxies and a total mass of about 10-17 suns. In that map, galaxy streamlines converge toward the vicinity of the Norma cluster, the observational heart of what had long been called the Great Attractor. Then the picture widened again. In 2017, Yehuda Hoffman, Daniel Pomerade, Brent Tully, and collaborators showed that the local bulk flow is not explained by attraction alone. Their Nature astronomy analysis found that the observed motion is shaped by two dominant large-scale features, a major attractor associated with Shapley and a major underdensity they called the dipole repeller, with the two contributing roughly equally to the CMB dipole. Their reconstruction also showed the bulk flow to be closely anti-aligned with the repeller out to 16,000 plus or minus 4,500 kilometers per second in velocity distance units. Exactly the kind of large-scale organization that makes the local flow field feel less like random drift and more like motion across a sculpted gravitational terrain. Hidden structure has also turned out to be real, not hypothetical. In 2017, astronomers reported the discovery of the Vela supercluster in the zone of avoidance, a major overdensity crossing the galactic plane at a mean recessional velocity of about 18,000 kilometers per second, showing that even in the 21st century, substantial mass concentrations relevant to local dynamics were still being uncovered behind the Milky Way's dust lane. The newest revision is even more destabilizing for the idea of a fixed cosmic address. A 2024 Nature Astronomy study using newer cosmic flows, 4 data reported a slight probabilistic preference for Laniakea not to stand as an independent basin after all, but to be part of a much larger Shapley Basin of attraction. The University of Hawaii summary of that same result put the odds at about 60%, meaning the scientific signal is not certainty, but a statistically meaningful lean toward an even larger structure than the one that redefined our home a decade ago. At the same time, the velocity catalogues themselves have become large enough that the anomalies are harder to dismiss as mere lack of data. Cosmic flows, 4 compiled distances for 55,877 galaxies, gathered into 38,065 groups, making it the largest release in that program to date. That matters because once peculiar velocities are measured on that scale, the question stops being whether there is enough information to see the flow and becomes whether the flow agrees with the standard model as comfortably as it should. This is also where the most controversial thread remains alive. Planck's own cluster velocity analysis found no evidence for the kind of giant all-sky bulk motion claimed under the name dark flow, and set a 95% upper limit of 254 kilometers per second for a blind bulk flow search. On those scales, concluding that its constraints are consistent with LCDM. Yet Kashlinsky and Atrio Barandella continued to argue in follow-up work that, when the filtering methodology is handled their way, a statistically significant dipole remains in WMAP and Planck cluster data. In other words, the mainstream result is a null detection, but the methodological dispute was never ended by a demonstrated blunder on one side. It was contained by the stronger consensus around Planck's interpretation. That is why the next surveys matter so much. Euclid, launched by ESA in 2023, is designed to map billions of galaxies out to 10 billion light-years across more than a third of the sky, specifically to trace large-scale structure and the roles of dark matter and dark energy with far greater precision than older catalogues could manage. If the present tensions are mainly due to incomplete structure maps, Euclid and the other new surveys should compress the residuals. If the residuals survive that increase in depth and sky coverage, then the motion of the Milky Way will keep pointing beyond a tidy explanation and deeper into the large-scale architecture of the universe itself. And that is what gives this motion its final weight. The core facts are solid, but the full explanation is still being assembled. The Milky Way's large-scale motion is real, anchored by the CMB dipole at roughly 600 to 630 kilometers per second, and the flow is organized enough that astronomers can map it into real gravitational basins rather than treat it as random drift. That is how Laniakea was defined, a flow structure about 160 mpc, or roughly 520 million light-years, across, containing about 100,000 galaxies and around 10-17 solar masses. From there, the verified picture becomes layered. The local flow is shaped by overdense regions in front of us and underdense regions behind us. The 2017 dipole repeller work showed that the dominant attractor associated with Shapley and the repeller associated with a large void contribute roughly equally to the CMB dipole, with the local bulk flow closely anti-aligned, with the repeller out to 16,000 plus or minus 4,500 kilometers per second in velocity distance units. That means our galaxy is not simply being pulled toward mass. It is also moving away from a profound deficit of mass. The map also turned out to be incomplete in places we could not easily observe. The discovery of the Vela supercluster in the zone of avoidance showed that a major overdensity had remained hidden behind the Milky Way's dust, crossing the galactic plane at a mean recessional velocity of about 18,000 kilometers per second. That is exactly the kind of result that makes the local velocity field feel more unsettling than it first sounds. Even now, astronomers are still finding substantial structures in regions directly relevant to the Milky Way's motion. Then came the newer revision to our cosmic address, using updated velocity field reconstructions. A 2024 study found a slight probabilistic preference that Laniakea may itself be part of a larger Shapley basin rather than a fully independent supercluster. The result is not final, but it matters because it pushes the same pattern seen throughout this story. Each time the map improves, the structure containing us tends to become larger, not smaller. The datasets driving this work are also no longer small. Cosmic flows, 4 compiled distances for 55,877 galaxies in 38,065 groups, making it one of the largest peculiar velocity resources assembled for this purpose. That scale changes the tone of the debate. The issue is no longer whether astronomers have enough information to detect coherent motion at all. It is whether the increasingly dense catalogues will make the remaining discrepancies disappear or make them harder to explain away. That is why the closing image of this story is not speculative so much as unfinished. Earth is moving, the Milky Way is moving, the local group is moving through a gravitational landscape that has already been partly mapped, partly corrected, and partly redrawn. The confirmed ingredients now include Laniakea, Shapley, the dipole repeller, and hidden mass concentrations such as Vela. The unresolved part is whether those ingredients are sufficient as they stand, or whether larger connected structure still sits behind the current boundary of the map. So the strongest ending is also the most honest one. Earth is moving towards something real, but what makes it stranger than expected is that the destination is not a single object. It is a hierarchy of structure basins inside larger basins, attraction balanced by repulsion, visible matter tracing a deeper dark matter framework, and each new verified survey has made that architecture more expansive, more precise, and less easy to reduce to one simple source.